there's currently no question in the chat. So then I would like to thank you again, Sabine, and we will move on. It's also time. Move on with Vito's talk. So Vito, can you please share your screen? I think Sabine has to close it first.
All right.
Thank you. Hi, Vito. Yeah.
Hi.
Let me briefly introduce Vito.
Can you see my screen?
Yes, I can see your screen. So Vito. Vito is a senior staff research scientist at Google, where he leads a research group on visual learning. He received his PhD from ETH Zurich, and then he was postdoc at India and Oxford, and he was back at ETH. And then he, in 2012, he became a faculty at the University of Edinburgh, where he also received an ERC starting grant, and then afterwards went to Google. He is probably most known for his work on object detection and also measuring objectness. And he received the Best Paper Award from the European Conference on Computer Vision. And today he will tell us something about his recent research on 3D deep learning. Looking forward to it.
Thanks, Andreas. Thank you for inviting me to give this talk. Yes, Andreas said I mostly worked on lots of 2D problems, but recently I moved on 3D deep learning. Actually, Andreas, can you keep the camera on so I can see that the connection is still working? Thank you. So this is a relatively recent mission for me, but I'm very motivated for it, so I'm happy to show you our early results. So the general objective is to being able to do scene-level 3D reconstruction starting from a single image. And here you would input an image, and you would like to reconstruct the shape of every single object in it, but also reasoning across objects, detect occlusions and resolve them fully, for example, by reconstructing the shape of the chair hidden by the table. And also resolving support relationships like the bottle is on the table. And maybe, perhaps, why not also material properties like the windows are reflective and the chair is wooden. Above all, we want a scene-level reconstruction so that all the objects live in a single common coordinate frame. They're all coherent in one scene. A big part of what we do in my team is to train from photorealistic rendering of 3D assets. This enables us to see samples of the association between local texture patches and 3D shape, but also examples of the 3D arrangements of objects and various properties like the materials and style. Also, if you think of it from a photorealistic standpoint of rendering, it raises the challenge to develop more generic differentiable rendering engines, for example, that could include interaction of lights between objects. And once you have such a tool, if the community will reach that, we will be able to do end-to-end training starting just from images instead of having the 3D assets. So we didn't solve this all, of course, but along the way, we have produced a couple of, I think, interesting results, which I'm going to show you today, starting from CoreNet, which is our first step towards getting a coherent 3D reconstruction from a single image. So here we make several contributions. We propose three improvements to common single object reconstruction architecture based on encoder-decoder, which improve their quality. And especially we make an extension that allows to produce a coherent reconstruction of scenes with multiple objects, coherent in the sense that all objects live in one coordinate frame and they don't interpenetrate in 3D. We also enable to evaluate on synthetic multiple object scenes, so you can really evaluate down to the shape reconstruction of multiple objects with two new syntactic datasets. Oh, there is lots of related work. So at a first glance, lots of work on single object reconstruction, typically focusing on representations like voxels, implicit functions, point clouds, or primitives. And we build a lot on two schools of thoughts here, the voxel grid school of thought and implicit function, which we are going to show, we are going to blend into a single approach. And we also go beyond by tackling multiple objects, but also by trying to look at what happens with higher realism. Often these papers are synthesized with just uniform background and local illumination. I'm going to show an attempt at having a higher degree of simulated realism. There are also fewer, but some works on multiple object reconstruction. Typically, these detect objects in 2D and then reconstruct the 3D shapes independently. Because of that, you cannot guarantee that the objects will not intersect in 3D. Instead, here we just reconstruct everything in a single pass through the network without relying on a detection stage, which leads to this coherent effect I was discussing. Also, Typically, most works don't evaluate 3D shape reconstruction in multiple object scenes because often they don't have the data. Now the SunCG is banned. And one thing we contributed here is to produce some synthetic data set of multiple objects so we can evaluate down to shape reconstruction in this case. Of course, there are exceptions to all these trends that I invite you to check the paper. So the starting point is voxel grid encoder decoder, where you input an RGB image and you produce an occupancy value on a 3D grid. Here, instead, we condition the 3D decoder on an offset that's provided and produce occupancy at points on this grid that vary according to this global offset. At test time, then, we can produce a reconstruction at higher resolution than the native decoder resolution by invoking the decoder multiple times with different grid offsets and every time determining another point near the previous ones. And then we can then take this high resolution grid, we reintegrate and extract geometry with marching cubes. So this is a good idea because it has the properties of voxel grids, which are translation equivariance, but also implicit function models, which means we can get high resolution with a fixed memory footprint. Our second improvement are ray trace skip connections. We reconstruct in camera space and assume we know the intrinsics, which often are given in the EXIF data, or you can find them in datasets like Pix3D or Matterport. And then we use this camera matrix to connect pixels or points in the encoder layers to corresponding 3D frusta in the decoder layers. Because of this, we can propagate local information from pixels to 3D, which is done in a physically correct manner. And this helps us get sharp reconstruction details. And this ray trace connection play well with this hybrid representation because you can now change exactly which points in the output volume are touched by the frusta, adjusting to the offset in the global grid we discussed before. Other improvements in IUU loss. What happens that because we are basically doing a classification problem of whether a point is inside an object or not, we could in theory use cross-entropy loss. However, the volume is mostly empty in these problems, which leads to high class imbalance. Also, we are more interested in overall object geometry rather than evaluating independent points. So we propose a generalization of the standard IUU metric for this case, where we replace the standard set operators with min and max, which allow us to handle the continuous output that the model produces typically, and also add support for multiple classes in a single image, which is the core of this talk. Unfortunately, I'm going to tell you later, when you add multiple classes, you get even more sparsity, even more imbalance, which we handle in this case as well. So now I told you everything about one object, so binary classification, but we can actually upgrade to multiple objects in the same image by predicting a multinomial distribution over classes at every point in the grid. And then we can pass this higher resolution reconstruction that we get from our representation by thresholding the probabilities as 0.5, which guarantees space exclusion, and also provides a continuous value for the marching cube to produce more smooth reconstructions. So in the end, we can get a joint reconstruction where all objects live in a common coordinate frame and do not interpenetrate in 3D. So these improvements I was mentioning help even more with a multiple object case. The hybrid volume representation brings translation equivariance, which is really useful in this case because objects can appear anywhere in space. They're not always in the middle of the volume. And also typically they occupy a smaller fraction of all the volume, so you need this fine-grained output resolution. The ray trace skip connections propagate occlusion boundaries and the contact points from 2D to 3D, and this helps understanding the depth relations among the objects locally. And when you get into multiple objects, the output space is even sparser because most of the C outputs of the model are 0, and so we alter the IU loss to balance for this sparsity. So quick view on experiments. We experiment on ShapeNet with 2 levels of realism, the typical one found in the literature with local illumination, simple forward graphics, a proper global illumination with the environmental map, ground plane, shadows, highlights, and also real images on Pix3D. And we propose a new data set of assembles of ShapeNet objects, pairs, and triples that allow us then to evaluate multiple object reconstruction. Here are some qualitative results from single object reconstruction. We can get hidden views of objects thanks to the prior in the network and thin structure thanks to the ray trace skip connections. You can see here, for example, we can get the hind leg of the chair. And quantitatively, we train many models, changing the loss, the use of ray trace skip connection, the level of realism. And the main messages are the ray trace skip connection helped by about 5% on MIUU, depending on the loss. And the IO loss really performed better than cross entropy or even focal loss. And surprisingly, results are slightly better, just a small margin, but consistently on high realism and low realism. We were a bit surprised, but we think it's because the better shading and shadows, they provide shape cues. In the paper, you can also find lots of experiments on surface metrics instead of volumetric metrics, where we observe similar trends, and lots of comparisons to state of the art. I also said we can reconstruct at a higher resolution than the native decoder output. And to prove this, we trained a native decoder at 32 cube and reconstruct up to 128 cube or 64 cube in the middle. And we show in the paper we lose very little performance compared to a native 128 cube. We also tried to go a bit crazy and try to reconstruct at 256 cube from a decoder that was native 128 cube. And in this case, we couldn't even compare because we didn't manage at Google at least to train a proper voxel grid at 256 cube. So it's kind of fun that you can go as high as that. We also have in the paper reconstruction results of real images on Pix 3D. And that is fun because it's a realistic data set of real images, not synthetic, where one object is associated to a ground truth 3D reconstruction that's manually aligned. And here you can see that we can handle bulky objects like sofas, but also thin objects like tables. And we are able to ignore the background clutter. And we also have quantitative comparisons to the state of the art in the paper. Finally, we get to qualitative results for multiple object reconstruction. Here you can see some example of a data set. We can see that the model is able to reconstruct the class, the shape, and the pose of all objects into one coordinate frame and reconstruct the occluded parts by other objects. And if we zoom in onto my favorite example, you can see here how the mag handle was cut in two by the bottle, but can be reconstructed by our method from another view. You can also have an innovative view from under the table, and that allows you to appreciate the globally coherent coordinate frame in which the objects are reconstructed. Here is another example. And in terms of results, again, we tried lots of combinations, changing the loss, ray trace skip connection usage, degree of realism. And the message here is that the ray trace skip connections help even more in the case of multiple objects, between 8 and 10% depending on the loss, which is what we expected. In theory, it should help more there. And the IO loss still performs best when combined with ray trace skip connections. And focal loss is almost as good, but cross entropy really doesn't work in this situation. Again, it's slightly better on high realism than on low realism. This brings me to the end of the first part, where I showed you 3 improvements of common single object reconstruction architectures. I showed you an extension to handle coherent reconstruction of scenes with multiple objects. And we also have these large-scale datasets, which we're going to release soon, with synthetic multiple object scenes. Now we can get to the second part, which is shorter, on conditional flow models for images and 3D point clouds back to one object at a time. So normalizing flow models have several advantages comparing to, the heroes of the deep learning era, like variational autoencoders, GANs, and perhaps also autoregressive models. They enable exact latent variable inference and log likelihood evaluation of every sample. And thanks to that, you can train directly for max likelihood, which is fun instead of a surrogate objective like in VAEs. Also, they are bijective in the sense that you can go from X to Z back to X without loss of information if you keep the latent space as high dimensional as X, like in practice is done. And you are able to do efficient inference and synthesis compared to autoregressive models much faster. And you also get this nice, well-behaved latent space, which is useful for downstream tasks, like, for example, VAEs are able to do, but not GANs. So what are normalizing flows? Here I show you the right part of the model going from Z to X. Normalizing flows are a series of invertible transformations, typically affine. And the crux is that the parameters of each of these transformations G is regressed by a neural network that operates on the data. And you can leverage a change of variable theorem to evaluate the exact locality of a sample. In this case, it would be here at ZL. So far, works have shown how to model the distribution P of X of the data. And what we did new is to enhance these models to be able to model conditional distributions of the type P of XB condition of XA. And in the example where XB is a point cloud and XA is an image, sampling from this conditional distribution essentially performs 3D reconstruction. So how does it work in a nutshell? So first, we build a regular normalizing flow models for XA, which has latent space ZA. So here is a sequence of invertible transformation G, whose coefficients are regressed by a neural network that operates on XA. Now the special sauce is on the tower for XB. Here, there are also affine coefficients for transformations F that also depend on XB, but additionally, they also depend on the same inputs to the transformations G at the same level of the network that were used to produce the coefficients of XA. So here, XB then depends both on ZB and ZA, and therefore also on XA, which generates this conditioning effect that we wanted. So now we can use this to do inference. We can just run a standard normalizing flow inference on the XA tower, going from X to Z. And now we store Z and all the intermediate results. This encodes the conditioning on XA. Now we can sample the latent variable ZB from a Gaussian, just as usual. And now we can run the reverse tower of XB, running all the inverse transformations Fi to generate XB condition on XA. And the trick is that all the necessary inputs to these transformations Fi are all pre-stored when we run inference on XA. So we have all the dependencies, we can just do it. And in doing so, basically XB, depends now on both Z and ZB, and XA depends only on ZA. And now during training, now we can train for the likelihood of the two samples together. Because of the structure of the model, we do direct likelihood of XA and the conditional likelihood of XB. And also optionally with an invertible cycle consistency, which I leave for the paper for those that are interested. So quick results on 3D reconstruction, going from an image to a 3D point cloud. In order to do this, we need one more techno trick on how to handle point clouds in normalizing flows. And I refer to the paper for that, but it's taken too much time to go over it. So here you can input an image, model that conditional distribution, and sample out a point cloud. And you can see here the beauty of the typical priors in such neural networks. Even from a chair from the back, you still get a plausible shape out. You get your missing legs reconstructed, like many works have shown it with other type of models. Now we can train a model for doing the converse conditioning, probability of an image condition on a point cloud. And if you sample out from that, you essentially do rendering. And because the model is fully probabilistic, every time you resample from that same distribution, you can actually get another image where the viewpoint changes a little, the texture changes, the shading changes a little. It's fun. I must admit, it doesn't look as good as a gun. It's early days, but to our knowledge, we are the first to show this done with normalizing flows. And there are also possibilities to do this for a variety of other problems with conditional structure, 2D problems, typical image to image. For example, sampling out an image condition on a segmentation mask, or the reverse, or the same for the segmentation mask not on a road, but on a building, or of even an earth view, or even painting in a shoe based on edges. And what I like about this result is that it's always the same model, just trained again, and that you get this probabilistic effect when the domain mapping is one-to-many, is ambiguous. For example, there are many possible street view images that correspond to the same semantic segmentation, or many shoes for the same edge map. You do get different samples every time. And when the domain is more unique, like, there is much fewer segmentation maps that match street view image, you get near identical samples every time. So now I get to the last part of the talk on neural rendering, which is, hope, the lightest and the most fun. Here, the goal is to try basically to replace Blender. So when you want to synthesize an image in computer graphics, you feed it some geometry, typically a mesh, in our case voxels, some material describing that geometry, and a lighting position, and maybe other effects. Then you pass it into Blender or Maya, or whatever you like, and you get a pretty image here with global illumination and all these nice effects. So we would like to have a rendering framework where instead of Blender, there is a neural network, which is controllable, where you can change the appearance, viewpoint, shape, illumination, and every time just run inference without retraining and get an image out. Why would you ever do that? You might wonder. We think it's useful for image editing, but also it's natively differentiable. So in the future, we might think of incorporating such a renderer into a learned 3D reconstruction pipeline. It's also very, very fast. This one runs unoptimized at 10 frames a second, which is much faster than running a proper global illumination ray tracer. So in practice, the problem is defined as follows. You provide a ground plane and a colored voxel object that also includes texture, and you can ask it to rotate it, translate in scale, change the lighting position, paint the object, or even add a texture to it, and every time just run inference and get an image out of the model. So there's lots of related work, but we fit squarely into this box of works that started from the seminal RenderNet, I would say, where you pass some geometry and you try to get an image out. And in that sense, we do better because we're able to handle very fine-grained texture. I'm going to show you later. And also we can alter the illumination detection, not just the viewpoint. And perhaps the kind of modern love, especially at Google, is this implicit representation type of works like NERF or earlier deep voxels, where you start from a set of calibrated images rather than a geometrical shape like we do. Start from a set of calibrated images and you're able to very accurately render novel viewpoints. So here the advantage of our method is that we're able to change also the appearance texture and the illumination of just the viewpoint, and that we don't need to train for every object. The disadvantage that we do need the 3D shape to start with. And the training setup of our method of input-output, you want to provide all these parameters that the user can change, the shape, the materials, and the light. But some parameters are fixed. There is always an ambient light, the ground is always planar, and there is a certain degree of specularity that's fixed. Then with these attributes, editable and fixed, you can render them with Blender to get training data. So then the problem becomes mapping from here. You can see my mouse, right? From here to here. So easy, simple initial formatting configuration. You pass your objects and you transform the world coordinate into camera coordinate according to the translation rotation scale the user required. And then the fun is, how do you provide materials? How do you specify the color of the voxels, essentially? So the simplest thing, you could paint over the voxels, that like in a painting tool. That's fun, but you will not be able to do very fine-grained things, just basically color the parts. More interestingly, you can do appearance capture. You can provide an image that's aligned with the 3D shape. And this allows you to transfer into much finer things like textures and fine-grained textures. And you can get this alignment either by an automatic method or by using datasets like Pix3D, where that's been done manually. Here is a quick fly over the network architecture. The color the voxels come into the 3D encoder that decreases the resolution and mashes together high-level features. And then at some point you pass through a reshaping operation that turns the width, height, depth times channel into width, height times depth channel. Basically what this does is an orthographic projection that preserves all the details of the depth information without throwing them away. You can then pass them through a resolution preserving 2D convolutions to get fine-grained shape and general scene structure features. Then you have another branch of the network that inputs the light position. And the light position, we process it through two lightweight, fully connected layers. And then, as the trick, we replicate and tile the light over a big feature map, which has as many locations as the voxel geometry feature map. And because of this, every point in the feature map has information about the light and is able to reason and reconstruct then about shadows and reflections and so on. So then we concatenate these two and pass them to a 2D decoder, that increases the resolution and produces the output image. And to train, we just train to emulate Blender. So now if you run this, it's cool because it gets you overall scene structure right with shadows and even highlights, but it washes out texture completely. Just somewhere along all our de-resolutions, we lost the texture. So here is a second version, a better version of our model where we take care of texture deliberately. So we start by adding a branch where we take these colored voxels and splat them onto a 2D image, just splat them down without taking care of light interactions, just projection preserving. So this is a nice image because it preserves fine-grained texture details, but it has a lot of artifacts. The viewpoint is not quite right? Because you acquired the appearance capture view from another view that the user wanted. And also you have aliasing and other effects. Now you pass it through the resolution preserving to the convolutional layers. And what you get here basically is fine-grained texture features, which you can then combine with these MVR features before, which had exactly the converse properties. They had proper scene structure, they had proper understanding, supporting the understanding of shadows, but they washed out the texture. Now you can combine the two, and then you can pass them through a unit that renders an image, which is now artifact-free, but also has a fine-grained texture. Again, the loss is always RGB reconstruction of Blender. So here are a couple of experiments on ShapeNet chairs and cars, and every time we test on different object instances that we were seeing at training time. And here you can see that we can capture illumination effects. Here is the object. You can change the light position. You can see the inset, the shading on the object changes and the shadows move accordingly. You can also get more complex effects like reflection on the ground, which normally belong to the global illumination realm. You can also get shadows of complex objects like the bulky part of the objects are uniform shadows and the holes are reproduced in the shadow. You can even have these multiple bounces of light where the color of the ground affects the color of the object and vice versa. So here are results based on the NVR model with a single color per object, where the model needs to reproduce shading, shadows, and reflections, but doesn't have to worry about texture. And here you can see the more difficult version where we also need to care about texture. Here is the input view, just one view that was given to teach the texture to the model. And then you can change camera, illumination, and so on. And here is a prediction that's made by the model that really reproduces all these nice effects of a standard rendering engine. You can see the shadows move along, the shading changes, the specularity moves, and all these textures are all new. They'd never were seen during training. In the paper, we have a ton of comparisons with alternative methods like RenderNet, single to multi-view, image translation. I recommend you check there. One fun thing that we really like of something like this is that you can edit the appearance of the object and then just run inference quickly without retraining to get this rendering. For example, here we change the ground from green to red. Here we change the polka dots from black to red. And here we put a picture of the author, Costantino Rematas, on the chair. Makes sense. And every time you can re-render, just running forward without retraining. You can also get natural illumination instead of this single vector XYZ light. You can put an environmental map and produce this nice soft shading and soft shadows. And again, the environmental maps can generalize from training to test nicely. And the very last result, so far everything was synthetic, but we can actually do appearance capture from real images. Here is on the Pix3D dataset where somebody actually aligned the models to the image, and you can capture, take away the texture from that image and then re-render from any other viewpoint, illumination, and so on. This brings me to the end of the talk, and I've shown you in this third part a controllable model where you can change object appearance and geometry and light, and every time just run inference to get a new image. We are able to properly deal with high frequency texture, which is maybe the main selling point, and we get this automatically learned interaction between certain elements like reflection, shadows, and even secondary bounces of light. Thanks for your attention, and I will take questions.
Thank you, Vito. Great talk. Okay, so the first question here in the chat is, what happens if you apply dropout to the texture condition image?
You apply dropout to the texture condition image. You mean this appearance capture image where we take the texture from, I guess?
I guess.
Dropout?
What happens if you apply dropout?
So that's okay. That's the coolest question I got in a long time because I don't really get it. But so I guess you could drop out some pixels from it or from the network layer.
Yeah. So that's he says yes. So that's what he means, I guess.
Wow. Well, I never tried it. I wonder what that would do. Maybe generalizes across texture even better because it doesn't, tune and fine tune and really overfit to that particular texture, I guess. But actually, we didn't try any data dropout. I mean, the model is trained with parameter dropout as usual, but I wouldn't have a good answer for any kind of data dropout. We didn't do it.
Mm-hmm. Another question, do you think this rendering step 3D voxels to 2D features is the right way for neural rendering, especially when scaling to more complex data?
Okay, so if it's a question about how we did it inside the model, then yes, I'm convinced it's the right way. But perhaps the question is more about, do we want to think of neural rendering as something that requires an input shape? Or should we think of neural rendering as just give me the images and I synthesize something else? So if it's the second part of the question, I guess it's more interesting. Let me interpret it as the second part. I think that the two worlds, these two things are really growing independently in the community, and they're really two sides of neural rendering. I think they're both useful. That's the truth. The more nerve style, just give me the images, requires less preprocessing because you don't need to get the shape, but it's difficult to make very controllable. As I was arguing, it's difficult if you make it so implicit to be able to start changing textures around or doing edits finer inside. But then, okay, you just need calibrated images. Maybe they're a little bit easier to get. On the other hand, you could reconstruct a shape from the calibrated images and fit into a pipeline like ours. But the reason why I care about going from shapes to this is that it enables me to reason explicitly about 3D, very explicitly, which on the long run, we will see if we manage in my team. But the long run plan is that we will be able to ask questions like inverse it, say which 3D shape would have generated this image, or even better, I give you an image, reconstruct some shape that will then re-render here and do it across a mixed supervision dataset. Do it across a dataset that will have For some type of objects, only images, and for some type of objects, also the 3D. And that is where I think scaling will come in. But yeah, I'm really selling you stuff that's 2 years out, right? Just explaining why the two sides are both interesting.
Good. Yeah, so I think the question could also, I had a similar question. So what do you think about representation? So certainly it's probably harder to get implicit models from CAD models, but you could do that, right? You could fit a implicit model to a CAD model, or you could sample points and get a point cloud. So maybe the question could also be understood in terms of like, do you think voxels are because voxels have some downsides as well, right? So in terms of resolution, scaling them to something that's really large, even with data adaptive structures is hard. So what are your thoughts on the ideal representation for neural rendering?
Absolutely. Sure. I was trying to defend the fact that I like something that's explicit in 3D because it allows me to do all those things. But this explicit thing in 3D doesn't have to be a voxel grid, obviously. I mean, in fact, in all our experiments, we start from meshes and then we just voxelize them to start from, right? Voxels are a convenient thing because you can spend your research time on other aspects than the representation, especially given so much nice work has been done on representation. But, you know, it doesn't have to be. No, absolutely. I mean, you could imagine doing, you know, by the way, another advantage of doing direct Blender emulation with direct input shapes is that you can also then parallelize rendering a lot more. But you could do all those things with implicit function model that derive from a mesh or directly meshes. I'm not very married to a particular representation, if that was the question. And I think in the future, on the long run, we need to be able to really hit the following golden trade-off. Preserve controllability and variability. So being able to say, okay, chairs vary in a certain way, but control, not just somewhere and we don't know what it is, but at the same time, not be so heavy like explicit voxel. Like, so this middle ground, there is lots of nice research. Don't think it's completely solved yet, but we really need to be able to have both. So if the community goes forward and we will have something very lightweight, but we cannot touch, I don't think we'll solve all of 3D reconstruction on the long run. There's something halfway and lots of work to be done.
Another question from Shara Ponsmo. In the neural rendering project, how dependent is the model to the specific object? How do you generalize it to, say, scenes or multiple objects, etc.?
There seems to be a double question. So that specific object, well, our experiments show that, you know, all the test objects were never seen during training in that sense. And we also show generalization across categories in the paper to some degree, but not well evaluated. Now, if the question is, do you need to have one object or can you have multiple objects? So we actually have results of multiple objects in a pending work, but will not be found in that paper. It gets harder and harder to learn light interactions. So when you have the ground plane and a 3D object, like I showed today, you have these nice light interactions I was showing you, the specularity, the cross shadows and reflections. But once you have 3-4 objects, it gets harder and harder to get to learn them all. So this is the state where we are now, and it makes sense given that it has to learn that implicitly. And yeah, I guess I'll leave it at that, not to sell more than I have.
Okay, so maybe final question here. I'm actually not exactly sure what it refers to. So I'll try to.
It's difficult to do.
Thank you, Vittorio, for the wonderful talk. Number one, when you reconstruct a full scene, is it necessary to have prior knowledge of every object in the scene? Can it go unsupervised? And then the second one, what is tricky when you switch to real-world object reconstruction?
Right, this points to the first part of the talk. Now we talk most about neural rendering, but yeah, in the first part of the talk on CoreNet. So about knowledge of every object in the scene. In our specific experiments, all the objects are unseen. They were never during training, and you don't know which ones appear, and you don't know which categories appear. But you know it's the same category you had during training. So you do have, it's a bit like in the object detection literature. You generalize in the sense of new instances and new compositions. All the compositions are new, but you don't, we didn't yet demonstrate in the paper you can generalize to new categories or new, you know. So in that sense, you have knowledge of the object in the scene, but it's limited. You only know what could happen and not what is in the scene, right? So in this sense, I don't think it's a particular limit. I would rather point to the fact that we show results until 3. We did try to go to 5, 7, 8, but it gets really a mess. So the ability to do compositionality with such a model is limited, right? So then we would need to think of other things. And then about unsupervised, yes, I mean, the first part of the talk, that has to be supervised with 3D shapes and images associated to them, like otherwise there is no way. But the general idea that you can go, from pixel patches to 3D, that can be learned in less supervised manners. There are papers in the literature and some by others. And often a direction I find attractive is to change the question. Instead of saying for the loss, oh, is this voxel at the right spot, or this polygon at the right spot, you can ask, is the image I re-rendered corresponding to the image I started from? And that is more the differentiable rendering type of training. And some of the differential renders to date, I think all of those that have shown such a result, they are more like emulating the rendering process kind of in a simpler manner, but very well, engineered right. And we are trying to go in the direction of trying to learn that process and use it then later for training unsupervised, but we will see if it works.
Fantastic. Thanks a lot, Vito. Thanks, everybody. This concludes the session. We have now a break until 4:30, the next session, so 45 minutes break, but we have prepared, as in the other breaks, fast forward videos, 1-minute videos of the main conference. So if you want to hang out in the YouTube channel, then you'll be able to watch these videos. So see you again in 45 minutes.